Welcome to next lecture. In the previous lecture, we discussed about MOSFET and IGBT characteristics, and up to the previous lecture, we can consider it was first chapter, okay, basics and power semiconductor devices. Now let us start the second chapter, that is basically rectifiers. Before that, let us have basics of or introduction for this converter analysis. So basically, now onwards, whatever the course we will cover all together will be treated as power electronic converter analysis. So power electronic converter is nothing but it will convert the given input power to match with output power. Okay. Suppose if both input and output powers are in the same form, like both are AC or both are DC, there is no conversion concept, but it is only controlling concept. However, all of these circuits can be considered under main subheading, that is power electronic converter analysis. Okay. Now in this, the first type of power electronic converter, that is AC to DC converters. AC to DC converters. Okay. As the name indicates, for these circuits, input is AC power and output is DC power. Okay. These circuits also known as rectifiers. These circuits also known as rectifiers. So output is DC power. That means basically average value of output voltage and current waveforms is non-zero, or it is a finite value. If you look into the Fourier series analysis, A0 by 2 term is a finite value, which is also called DC component or average value. Okay. So rectifier is a first category. It will convert basically AC power to DC power whose average values of output voltage and current are finite values. Okay. Now let us look into second category, that is DC to DC converters. That is DC to DC converters. Okay. So here, as the name indicates, for these circuits, input is DC power, output is also DC power. Okay. And as output is DC power, average values of V0 and I0 are finite values. Now in this particular DC to DC converters, these circuits in high power applications, these circuits are referred as chopper circuits, and in low power applications, these circuits are referred as SMPS or SMPC, switched mode power supply or switched mode power conversion. Okay. Next, third category, DC to AC converters. DC to AC converters. Okay. So in these circuits, as the name indicates, input is DC power, output is AC power. Okay, output is a AC power. What do you mean by AC power? Average value of V naught and I naught are 0. V naught and I naught will have some phase differences. Because of that, the output power will be finite value. These circuits are also referred as inverter circuits. Okay. So generally, one misconception is people will feel that converter is doing AC to DC conversion, inverter is doing DC to AC conversion. But strictly speaking, as I told in the beginning, all of these converter circuits, all of these power electronic circuits are classified under the main umbrella power electronic converters. Okay. But on what basis you should specify that it is a rectifier and inverter? If the power flow direction is from AC circuit to DC circuit, then we should refer that circuit as rectifier. If the power flow direction is from DC circuit to AC circuit, then that circuit should be referred as an inverter circuit. Okay. Sometimes the same circuit will operate either both rectifier as well as the inverter, right? So one example later on we will see, but at this stage just to complete the statement, single phase or three phase full converter or fully controlled bridge rectifier will also operate as inverter circuit under some special cases. Okay, once the converter analysis started, we will understand in detail. Now let us look into fourth category of converters. Fourth category of converters, that is AC to AC converters. AC to AC converters. In this, first category is AC voltage regulator. First category is AC voltage regulator. Okay. So AC voltage regulator, what is the definition here? AC voltage regulator. For these circuits, input is AC power, output is also AC power. Okay. As output is AC power, we can say average value of V naught and I naught will be 0. But what is the nature of the output? This particular circuit will be used to produce variable voltage and fixed frequency. Okay, output side variable voltage, but frequency is a fixed one. Now second category in AC to AC converter, that is cycloconverter. Now follow carefully here. I am listing out all converters, whether all of these topics are in the syllabus or not, one by one exam point of view I will tell you. Okay, so this is a classification of all power electronic converters. Cycloconverter. Cycloconverter, let me write CC. Input is AC power, output is also AC power. So AC power means average value of V naught and I naught will be 0. But basically cycloconverters are used to control the frequency. In other words, variable frequency. Of course, cycloconverters output voltage will also have variable nature, but the output voltage waveform is very complicated waveform. Harmonic analysis is very complex. Therefore, mostly cycloconverters are used for frequency control only, not for variable control. But variable voltage, variable frequency, cycloconverter drives was the old technology. Present days, inverters are using much popular. Basically, those are the PWM inverters. Okay. Next, fifth category is resonant converters. Resonant converters. Okay. So basically the resonant converters, there are two types: zero current switching, ZCS full form, zero current switching, and ZVS, zero voltage switching. Okay. This particular topic comes under soft switching techniques. Soft switching techniques. Soft switching techniques. Okay. Sixth one, basically it is not a converter, it is an application of power electronics, but very popular subject title is power electronics and drives. Therefore, let me write here itself, electric drives. So depends on the application and mission to mission, different types of these power electronic converters will be used. Okay. So this is about total power electronic converter circuits, right? Now in this particular category, some circuits are not there in the GATE syllabus, right? Some circuits are there in the engineering services syllabus. Of course, our course module is for GATE exam, but I will tell you what topics you need to prepare extra if you are going for engineering services exam or PSU exam. Of course, PSU exams, the depth in the questions not that much level, but the wider syllabus. Okay, I will write down clearly here. AC to DC converters. Of course, even though it is mentioned as a one converter circuit, this is very big topic, right? Single phase and three phase rectifiers, it covers majority of the course. So this particular topic is present for both GATE exam and engineering services exam. Okay, I can write one more letter also, GATE, engineering services exam and PSUs also, right? So that P stands for Genco, Transco, Discom exams, like that. And ISRO or CSIR, any different competitive exams you are preparing, you will get a questions from this particular chapter. Okay. Next, choppers. This particular topic is present for GATE, engineering services and PSU exams. Next, SMPS topic, this is present only for engineering services exam. Even for Genco, Transco, Discoms also, we need not to prepare this particular topic. Therefore, for engineering services exam in this particular category, SMPS is additional topic, right? If you are preparing for GATE or PSU, only choppers is sufficient. Next, coming to inverters. Inverters is also popular circuit, GATE, engineering services exam and PSUs. This particular topic, both single phase and three phase inverters, voltage source and current source inverters are present for all the three exams, and that too important topic also. Now coming to AC voltage regulators. Okay, of course this is a strictly speaking one controversial discussion, right? Of course before GATE 2020 exam, strictly speaking this word is not there. AC voltage regulator word is not there in the syllabus. Even at the present syllabus also it is not there. But last year GATE 2020 exam, one question was given from this particular topic. But luckily for that particular question, okay, marks to all was given. So here my doubt was, there was one mistake in the data also. Whether they gave marks to all because of that mistake or out of syllabus, that is not clear to me, right? Therefore, instead of taking a risk, I can say that you can prepare this particular topic for GATE exam, engineering services exam and PSUs also, safe side, right? AC voltage regulator, that is not a big topic. You can have very good understanding once you clear in the rectifiers chapter. Next, cycloconverters, you need not to prepare this topic for GATE exam. In the previous GATE questions, if you see, there is no question from cycloconverter topic. But this particular topic is better to prepare for engineering services and PSUs like Genco, Transco, Discom exams. Resonant converters, this particular topic is for engineering services exam only. This particular topic is for engineering services exam only. Okay, this is one extra topic. Electric drives, this particular topic you should prepare for engineering services and PSUs, right? So on this board, what are all power electronic converters are there in the literature. From now onwards I wrote these terms, okay, and what type of exam you are preparing, accordingly you can select, okay. So if you are preparing for gate exam, your focus should be single phase and three phase rectifiers, next DC to DC converter choppers, next inverter circuits, and a little bit about AC voltage regulators. And if you are preparing for engineering services exam and PSUs, you have to prepare all the topics. But particularly for Genco or Transco exam, you need not to prepare SMPS or SMPC. That's all. So SMPS or SMPC is not required for this PSU exams. Okay, this is the overview of power electronic converters. I hope it is clear, the bigger picture, right? Now, before moving further, one basic common point in this total circuits analysis, whether input or output, okay, you take any one converter. Basically, I can say this is the analysis of AC and DC waveforms. Whether you take rectifier, inverter or cycloconverter, AC voltage regulator, any circuit, it all basically involves the analysis of AC and DC waveforms. Therefore, before jumping onto this converter analysis, first let us look into the basic properties of AC and DC waveforms. Okay. Now let us look into AC and DC waveforms properties as a comparison table. Okay. Now just at the first observation, let us take ideal AC waveform. Okay, that is basically a sinusoidal waveform. Sinusoidal waveform is universally accepted waveform. And if you recollect our previous basics classes, we told that power electronic circuits consists of power semiconductor devices. They will operate as switches. Due to switching operation, what we discussed, the waveforms will be deviated from sinusoidal nature. The waveforms will be deviated from sinusoidal nature. Therefore, let us take one square wave just for illustration. Okay. In fact, in our previous classes in the Fourier series analysis, we derived Fourier series expression for this particular waveform. Therefore, it is meaningful to take this as an example. Okay. Now, suppose the positive magnitude is x, negative magnitude is minus x. Okay. And let us take this is a pi and this is a 2 pi. Therefore, can you recollect what is the Fourier series expression for this particular function? DC component is 0, therefore no need to write a0 by 2 term, and this particular function, from our earlier derivation we concluded that this particular function contains all odd harmonics. So sigma n is equal to 1, 3, 5 and so on, and 4x upon n pi multiplied with sine of n omega t. So what is that Fourier series will tell you. That is, this particular function contains all odd harmonics. For example, if I write RMS value for this overall series, what we will get? XR square is equal to, we can write it like this, x1 square plus x3 square plus x5 square and so on, where x1 is RMS value of fundamental component, x3 is RMS value of third harmonic, x5 is RMS value of fifth harmonic, and so on. So I can say here x3, x5, x7 and so on can be represented with xh square, where xh is RMS value of harmonic component. Okay, how can you express that? Xh, I can write it like this, under root xr square minus x1 square. Okay, square root of xr square minus x1 square will give you harmonic content, RMS value of the harmonic component. But what is useful term in this sequence of series? Fundamentally is the useful component. Therefore, I can write here xh upon x1. Okay, that means harmonic component is expressing as a ratio of useful component, that is fundamental. Okay, this particular ratio is known as THD, total harmonic distortion. Okay, total harmonic distortion. Now, one more thing is ratio of RMS value of the fundamental component x1 divided by RMS value of the overall function x1 upon xr will be referred as distortion factor. It is denoted with the symbol df. Okay, now we can express total harmonic distortion in another way. What is that? Suppose if you pull this x1 term inside the root, then what you will get? xr divided by x1 whole square minus 1, square root of xr divided by x1 whole square minus 1. Okay, so xr by x1 is nothing but 1 by distortion factor. Therefore, total harmonic distortion can also expressed as root of 1 by df whole square minus 1. Okay, so these are all the properties of AC waveforms. Okay, pure AC waveform and non-sinusoidal AC waveform. Now, what is point to be highlighted in this discussion? Suppose if you take ideal AC waveform, we can say that there is no harmonic here. So I can write for ideal AC waveform, harmonic content will be 0. If harmonic content is 0, we can also say that RMS value of the overall function is equal to RMS value of fundamental component. Okay. Next, if xh is equal to 0, can you tell me what is THD? THD is equal to 0. And if xr is equal to x1, what is distortion factor? Distortion factor is equal to 1. Okay, so these are the properties of ideal AC waveform. Okay, these are the properties of ideal AC waveform. So going forward in the analysis, if you come across AC waveform but it is not a sinusoidal function, then you have to calculate RMS value of the overall function and RMS value of the fundamental component. From where you will get RMS value of the fundamental? From Fourier series analysis. With that reason, in our beginning lectures, we did Fourier analysis for some standard repeated waveforms. Okay, we will use all of those conclusions for this particular topic to understand. So, with these values, what is the final performance measures we will calculate? That is total harmonic distortion and distortion factor. Okay, this is what our analysis direction. Now, all of these points about AC waveform. In the similar line, let us look into a DC waveform properties. First, let us take a pure DC function. A voltage or current magnitude is of always constant. Now, let us take output voltage of some particular function. Okay, let us do one thing. Just like x we followed in the previous explanation, here also let us follow x of t. Okay, so this is output of Fourier rectifier circuit. At this time we have not yet discussed. Just let us take this function because we did Fourier analysis for this particular function. Okay, and let us take this magnitude is x. Now how can you write Fourier series expression for this particular function? X of t is equal to average value, what you got, 2x by pi plus sigma even values of n. Okay, even values of n, 4x by pi multiplied with 1 minus n square into cos of n omega t, into cos of n omega t. Now I would like to write RMS value for this particular series. Then how to write xr square? Okay, xr square is equal to, now 2x by pi term I can write it as xdc square plus, here only even harmonics, whether it is sine or cos, RMS value expression will be same, x2 square plus x4 square and so on. x2 square plus x4 square and so on. Okay, now one important point to understand here, what is x2, x4, x6 and so on? These are harmonic components. If you recollect our basics lectures, harmonic definition, what we discussed, harmonic is high frequency component. Fine. You can also say that it is an integral multiple of fundamental frequency of sinusoidal variation. x2, x4, x6 and so on, these are all harmonic terms. Harmonic term is nothing but sinusoidal variation component. Therefore, we can say the given function, of course it is a DC function, no doubt in that, but the given function contains AC component also. Okay, the given function contains AC component also. That is what harmonic. Follow carefully. AC content in DC waveform, AC content in DC waveform is called ripple. AC content in DC waveform is called ripple. So how to find RMS value of the ripple component? It is just nothing but RMS value of the harmonic component in the AC discussion. But here RMS value of the harmonic component, there is a special name for that, that is ripple component. So we can write RMS value of ripple component is equal to under root xr square minus xdc square, RMS value of the overall function square minus average value square, total under root. This particular value is called RMS value of the ripple component. There is one question in TYC 1.1, you have to use this formula to solve that problem. Hope you understand this, what problem I am referring. If this RMS value of the ripple component expressing as a ratio of average value, that is DC component, such a ratio is called ripple factor. Such a ratio is called ripple factor. Now you can also express ripple factor like this, xr divided by xdc whole square minus 1, xr divided by xdc whole square minus 1. Now what is RMS value to average value ratio is called, that is form factor. Therefore ripple factor we can also express it as under root form factor square minus 1. Okay, now for example, if the waveform is ideal DC waveform. So what we can say that there is no AC component in this. Therefore, I can write here ripple component is equal to 0. Okay. So it will give you that RMS value is equal to average value. XR is equal to XDC. Okay. And if XR is equal to XDC, what is ripple factor? Ripple factor is equal to 0. And in other words, XR is equal to XDC, form factor is equal to 1. Form factor is equal to 1. This is very important table and very good start to understand the basics. Therefore, going forward, depending on the converter analysis, whether AC side or DC side, whatever side you are dealing, if you are dealing with the DC side, two factors are important for us. What is that? RMS value of the overall function, average value of the function. If you have these two values, ripple factor and form factor are nothing to calculate. In the similar way, if you are dealing with the AC waveform, you should have RMS value of the overall function and RMS value of the fundamental component. Therefore, converter analysis, okay, the bridge point or a basic building blocks or AC or DC waveform discussion. From this, again, final takeaway is average value of the function, RMS value of the overall function, okay, and RMS value of the fundamental component. That is the reason we spend good amount of time in the beginning basics classes how to find average RMS values of the functions and how to find RMS value of the fundamental component, that is from Fourier series analysis. That was the reason to discuss about those components in the basics classes. Now once we started converter analysis, our focus will be to use those conclusions. Okay, wherever I get average or RMS values need to write down, then we need to use those conclusions. Now with this a basic review, let us start AC to DC converters, and this chapter is very interesting. Follow carefully. Even though I am providing detailed lecture notes, my sincere suggestion is before going through that notes, first when you are watching the videos, draw the waveforms on your own hand. Otherwise, it is impossible to understand the subject. Okay. Of course, you may have a counter question, sir, whether in the objective exams do we need to draw waveforms in the exam? Until unless you are able to draw waveforms with your own hand, I am again stretching, with your own hand, you cannot answer any single question from power electronics. Okay. My lecture notes is just for helping only. When you are listening the classes first time, my sincere suggestion is draw waveforms with your own hand. Again I am stretching, with your own hand. Now let us define this AC to DC converter formally. Okay, AC to DC converter is also called a rectifier. What do you mean by that? For this particular circuit, input is AC power, output is DC power. Output is a DC power. That means average value of V0 and I0 are finite values. Average value of V0 and I0 are finite values. Here follow one notation very carefully. Throughout the lecture now onwards, even these symbols also really matter. Okay, that is why I am telling, if you are writing with your own hand, then only you will get practice. Output side DC components, right? Therefore, I will use capital letters to represent average values. Capital V0, capital I0, that suffix O, this is O, not 0. The suffix O indicates output, okay, output, the first letter of output. So average value of output voltage and output current waveform. Let me write down clearly. Average values of V0 and I naught waveforms. You need to write down in this way. Okay, if you are seeing the notes, you will not get that practice. So small v naught and small I naught are used to represent instantaneous values of the given function. So don't write capital V or small v casually as per your wish. Okay, follow this notation strictly to understand the subject. In the input side, AC, hence RMS values are important. Source voltage, source current, RMS values, capital letters. Okay, so let me write down clearly here. RMS values of Vs and Is waveforms. RMS values of Vs and Is waveforms. Okay. So how to define the rectifier circuit formally? Rectifier circuit will convert AC power to DC power, whose average output voltage and the current are finite values. Okay, depends on the circuit topology. Sometimes you cannot control, sometimes you can control. Okay, we will see that classification after this definition we will discuss. Next one is applications. In the introduction lecture, means our first lecture, we listed out applications of power electronics. Okay, but now this particular topic is application of rectifier circuits specially. Okay, the first application is, you can say that, battery charging circuits, right? All of us have these circuits, battery charging circuits. If this battery charging circuit is not there, you cannot watch our videos also. Your mobile, every electronic items need charging circuit. Basically, a rectifier is the charging mechanism. Second one is speed control of DC motors. Second one is speed control of DC motors. Okay. Next. Third one, electric traction. Third one is electric traction. Okay, because in electric traction, if you consider a mainline system, the source voltage is a single phase 25 kV AC system, isn't it? And the popular motor is DC series motor. In such cases, rectifier plays an important role. Next, fourth application is HVDC transmission circuits. Fourth application is HVDC transmission circuits. Fifth application is to provide DC power to inverter circuits. Okay, this fifth point we will understand it clearly again in the inverters chapter. Basically, inverter circuits, from the previous definitions, input is DC, that DC power will be provided by this rectifier circuits. Okay, next, sixth one is in renewable energy systems. In renewable energy systems. Okay, especially wind turbine controls. Especially wind turbine controls. There is one AC to DC converter. These are few and important applications of AC to DC converters. After this, let us start what are different types of rectifier circuits. Now, next topic will be types of rectifier circuits. Now, let us look into the classification of rectifiers. Basically, rectifiers are classified into three categories. The first one is uncontrolled rectifiers. Uncontrolled rectifiers. Okay, and the second classification is fully controlled rectifiers. Second classification is fully controlled rectifiers. Okay, and third classification is half controlled rectifiers. Half controlled rectifiers. Okay, now let us look into the what is the basic definitions here. Now uncontrolled rectifiers means, now we will follow our earlier symbols notation. What I told, capital V naught, by this time you should understand and follow that. Capital V naught is the symbol used to represent average value of output voltage. Okay, now onwards I will not write a full word. Capital V naught, that symbol itself indicates average value of output voltage. V naught cannot be controlled. V naught cannot be controlled. Okay, and V naught depends on source voltage only. Average value of output voltage depends on source voltage only. These circuits are designed with diodes. These circuits are designed with the diodes. Okay, next. Fully controlled rectifiers. In these circuits, V naught can be controlled in full range. Full range means negative value to positive value. When any function is changing from negative side to positive side, it has to cross 0. Okay. Now in this particular circuit, some topologies will have 0 to plus V naught, some circuit will have minus V naught to plus V naught, all together classified under these basically controlled rectifiers. V naught depends on one aspect is source voltage, no doubt about it. Next, another point is control features. How can you get a controlled feature? Obviously by using controlled switch or controlled power semiconductor device. Now if you recollect from earlier basics and power semiconductor devices analysis, at one particular stage we told that for AC circuits the best preferable device is a SCR or a thyristor. Okay, people used to say thyristor also, strictly speaking SCR, because GTO also comes under this category, right? So SCRs are popularly used in the rectifier circuits. Okay, now SCR can be controlled with a gate current pulse. SCR is a latching device. It can control with a gate current only for a short duration, hence it is called gate current pulse. The angle where gate current will be supplied to SCR is denoted with the symbol alpha. Most of the books will follow alpha as a symbol. Okay, this alpha is called either triggering angle or firing angle. It is also called delay angle, but the popular terminology is firing angle or firing delay angle. Nothing wrong to use these words. So these circuits are designed with SCRs. These circuits are designed with the SCRs. Now let us look into half controlled rectifiers. V naught can be controlled in half range only. Half range only. So half range means 0 to plus V naught. Okay, half range means 0 to plus V naught. Now V naught depends on Vs and alpha. Here also SCRs will be used, hence it is a alpha. Next, these circuits are designed with SCRs and diodes. SCRs and diodes. Okay, this is what the basic definitions. Now, these half controlled rectifiers, also known as semi-converter circuits. Okay, another terminology is a half controlled converters is also known as semi-converter circuits. Next, these two circuits together named as PCR, phase controlled rectifier circuits. So follow the terminology and the notation carefully. This is about basic definitions of uncontrolled, fully controlled and half controlled rectifiers. Next subcategory, based on source, these circuits are subcategorized into single phase and three phase. This classification is based on source. In the similar manner, here also we will have single phase and three phase classification. Okay, semi converters also single phase and three phase. Semi converters also single phase and three phase. Next, so this further second classification is based on the nature of the source. Next, based on the circuit topology. Topology means the way how devices are connected. Topology. Okay, these are further classified into half wave and full wave. HW indicates half wave, FW indicates full wave. Okay, next, full wave are further classified into two categories: center tap and bridge configuration. Center tap and bridge configuration. Okay, this is a subdivision. Next, three phase are further classified into half wave and full wave. This full wave is bridge category. Full wave is of bridge category. Okay, full wave is of a bridge category. Now, in the similar way, here single phase is further divided into half wave and full wave. Full wave is further divided into center tap and bridge configuration. Center tap and bridge configuration. Now, this three phase half wave and full wave, this full wave bridge connection. That full wave is a bridge connection. Now, coming to semi-converter circuit, single phase and three phase. Okay, and these are both are of the category full wave type. These are of the category full wave type. Half control and half wave both are different. And this full wave contains bridge connection. Here also it contains a bridge connection. This is about the overall classification of rectifier circuits. Okay, next, there is another way to look into these circuits, that is based on the number of pulses. Okay, what is that? Let us see. Now, here rectifiers can also referred as n pulse converter. N pulse converter. Okay, so for this n pulse converter, for example, input frequency is a Fi. Output frequency can be referred with n into Fi. Okay, output frequency is referred with n into Fi. Now observe carefully here, we are telling that rectifier circuit output is a DC. But at the same time, I am defining output frequency. What do you mean by that? Let us see. This can be explained by taking one example. For example, let us take input voltage is a sinusoidal waveform. Input voltage is a sinusoidal waveform. Okay, you can represent with the Vi or Vs. I will follow Vs, source voltage or input voltage, your wish. Now I will show output voltage of one particular rectifier circuit. Output voltage of one particular rectifier circuit. That is something like this. Now observe carefully. I want you to answer how many pulses are there in the output voltage. Remember, the number of pulses in the output voltage by the time source voltage completes one cycle is referred with this number n. Okay. Now in this particular waveform example, I can say that n is equal to 2. I can say that n is equal to 2. Now if you recollect from our earlier discussion, earlier we told that this particular V0 waveform is a DC. However, it has a ripple component. It is not a pure DC. It has a ripple component. Remember carefully. At the first stage of rectification, output voltage of any rectifier circuit is not a pure DC. It is in this particular type of waveform is called pulsating DC. This particular waveform is called pulsating DC. What do you mean by pulsating DC? This waveform contains ripple component. So the ripple frequency is referred with this F0. The ripple frequency is referred with that F0. So how can you define output ripple frequency? N multiplied with Fi. Okay, what is N here? Number of pulses when the source voltage completes one cycle. So for this particular example, what is N value? That is 2. 2 multiplied with input frequency. Suppose in the exam, input frequency is given to you, you have to take that value. Otherwise, you are allowed to take grid frequency of your country. Okay, so what is our Indian grid frequency? That is 50 Hertz. Therefore, I can write here 50 is equal to 100 Hertz. Therefore, finally, what is the conclusion? The output ripple frequency of 2 pulse converter is 2 times input frequency, that is 100 Hertz. Therefore, with this particular way of looking the rectifier circuits, I will write down numbers for all of our earlier classification. Let us look back into our earlier classification. Okay. Now here I will write these number of pulses in the output voltage. If you see this circuit, what is this circuit? Single phase, half wave, uncontrolled rectifier. This circuit has one pulse in V0 waveform. Okay. Therefore, number of pulses or this circuit is referred as a one pulse converter. In the similar way, I will write down the numbers. Single phase full wave circuit, full wave uncontrolled rectifier, in center tap and bridge connections, it will have 2 pulses in V0. Hence, it is 2 pulse converter. 3 phase half wave, it is 3 pulses, and here 3 phase full wave, it is 6 pulses. Now, single phase controlled rectifier, in half wave it is 1, full wave it is 2. Okay, and 3 phase half wave it is 3, and here it is 6. Here it is a 6 3 phase full wave. Single phase semi converter, it will have 2 pulses in the output. 3 phase semi converter, it will have either 3 or 6. It will have either 3 or 6. Follow carefully. In the entire rectifiers classification, in this entire rectifier family, the only circuit which contains either 3 or 6 pulses in the output voltage waveform, that is three phase semi converter. Okay, let me write down this conclusion clearly. Now let us write down that conclusion here. Number of pulses in V0 of three phase semi converter is equal to 6 when alpha is less than 60 degree. Okay, this number is equal to 3 when alpha is greater than or equal to 60 degree. We will see these reasons in detail once the waveform analysis is started. Okay, so this is what the overview of rectifier circuits. We will study all of these circuits in detail with the waveforms and complete mathematical analysis. Let us look into what are the basic categorization of loads that are used in the rectifier circuits. So the loads are broadly classified into two categories. One is voltage stiff loads. One is voltage stiff loads. Okay, and the second one is current stiff loads. The second one is current stiff loads. Okay, second one is current stiff loads. So in this particular first category, output voltage and output current waveforms. Okay, I am writing small letters. V0 and I0 waveforms are similar in waveform shape. V0 and I0 waveforms are similar in waveform shapes. Okay, so that means both V0 and I0 will have peak values, yet both V0 and I0 will have peak values at same instance. Same instance. On the other side, V0 and I0 are different in waveform shapes. Both will have their own waveform behavior. Okay, we'll see the reasons. That is, V0 and I0 will have peak values at different instants. At different instants. Okay, V0 and I0 will have peak values at a different instants. Now if you look into examples for this particular category, a resistive load and RE loads are considered under first category. Okay, now here examples: pure inductive load, RL load and RLE loads. Okay, RLE loads with sufficiently large inductance. We will come across all of this terminology in the later analysis stage. Okay. Pure inductive load, RL load and RLE loads with sufficiently large inductance will be classified under these current stiff load categories. Now, for example, when you are dealing with a resistive load, output power should be calculated with RMS voltage or RMS current. VOR square divided by R. In other words, IOR square multiplied with R. Whereas, if you are dealing with RE load, then output power can be calculated with E into I naught plus IOR square into R. In this particular case, this I naught is average value, this IOR is RMS value. Remember carefully, you should not use average and RMS values as per your convenience. You have to use as per the definitions. Okay. Now, in this particular case, output power should be calculated by using both average values. These two are average values. Okay. So, depending on the load which we are dealing, accordingly you have to use either average value or RMS value. Okay. These are the basic definitions. Next, see, whenever we are analyzing any circuit, okay, directly it is not good to have hardware implementation. First, we should analyze the circuit on paper with the theoretical aspects. But theoretical aspects, by considering all different practical scenarios, it is highly difficult. Therefore, in order to simplify the analysis, we will have some assumptions. Okay. In the similar way, what are the assumptions involved in the rectifier analysis? So, the first and foremost assumption is source voltage is assumed to be pure sinusoidal. Okay. Source voltage is assumed to be pure sinusoidal, right? So why? Because for any rectifier circuit, input voltage generally will be taken from power system grid. The grid can be modeled as an infinite bus system. What do you mean by infinite bus system? Under any conditions, means under any disturbances created in the system, power system, the sinusoidal nature of voltage source waveform will not be disturbed. That means if the positive half cycle it has, let us say 100 volt, negative half cycle also it will have 100 volt with a negative magnitude. Positive half cycle duration, for example 10 millisecond, negative half cycle duration is also 10 millisecond. So that our Indian grid frequency will be 50 hertz. Okay. So in order to analyze any circuit, you should have some base. That base for rectifier analysis will be sinusoidal source. Okay. Next, the second assumption is devices are assumed to be ideal. Okay. Devices are assumed to be ideal. What do you mean by ideal devices assumption? In conduction state, forward voltage drop will be assumed to be 0. In blocking state or turn off state, leakage current through the devices will be assumed to be 0. In switching, okay, in switching, recovery times TRR in case of diodes and TQ in case of thyristors. will be assumed to be 0. Switching times basically we are neglected. Okay. So, but coming to the practical scenario, devices will have these non-idealities. But for our analysis to be simplified, these non-idealities will be treated as a 0. Okay. Next, third assumption is load parameters are assumed to be constant. Load parameters are assumed to be constant in their entire range of operation. Okay. So with these assumptions, now we can start our rectifier analysis. Now let us recap. Source side voltage is a sinusoidal waveform. Devices are ideal. Load parameters are treated as a constant. You will have this type of assumption even in the control systems also. What is that? A linear time invariant system. Circuit constants or circuit parameters are treated as constants with respect to time. Now let us take the first circuit. Single phase half wave uncontrolled rectifier. Okay. And in this case, first let us take resistive load as an example. Resistive load into consideration. Now here this is a sinusoidal source voltage. Let us represent Vs is equal to Vm sin omega t. And let us take the source voltage terminal names with symbols A and B. And this is a diode. Voltage across this diode can be represented with a symbol Vd. See, if I write a small letters, that represents instantaneous values. Load terminal are taken as a X and Y. Between X and Y, a resistor R is connected. That is a load resistor basically. And output voltage is measured across the terminals X and Y. So V0 means output voltage is measured as X with respect to Y. And load current, that can be denoted with a symbol I0. Okay. So in this particular circuit, that I0 is a series circuit, hence total current, whether I0, IS, ID, all are same. Now this is the basic circuit diagram. From this, let us look into what is the working principle of this particular circuit. Now I have readily drawn the source voltage waveform. Here this is a PS, source voltage waveform, and the peak value of this source voltage waveform is, this is Vm. Okay, so that this waveform equation is Vm sin omega t. Now here x-axis is measured in omega t. That means units for omega radian per second multiplied with second. Okay. Therefore, second and second will cancel out. Then we will get units for x-axis in radian. Therefore, this is 0, this is pi, and this is 2 pi, and this is 3 pi. This is a 3 pi. Okay. Now the first waveform, of course, anyhow, source voltage is just for reference. Now the first waveform in the analysis, if you give this type of source voltage waveform to this half wave rectifier circuit, then what is the diode behavior? From 0 to pi, due to this positive half cycle of source voltage, diode will be forward biased. Diode is uncontrolled device. It doesn't require any control signal in order to turn it on. Then what will happen? The moment when it is forward biased, it will start conduction. Okay. And as per our earlier assumptions, we assumed that when the device is in the on state, voltage drop across the device is a 0. Therefore, from 0 to pi, when the diode is forward biased, I can say that load terminal X will be connected to source terminal A. So voltage across XY terminals will be just same as that of AB terminals. Therefore, the entire positive half cycle of source voltage will appear towards load side, and hence the peak value of source voltage and peak value of output voltage waveform both are same. Okay. Next, in order to draw output current waveform, this is I0 waveform. We just need to look into the equation for I0. Okay. Now, for example, if diode is on, if diode is on, what is the basic circuit equation here? XY terminal voltage, that is R into I0. This is equal to source voltage Vm sin omega t. Therefore, from this we can write I0 is equal to Vm by R sin omega t. Now observe carefully. Equation for I0 in this particular resistive load is exactly same as that of source voltage Vm sin omega t. Only the difference is this particular magnitude Vm by R. Therefore, we can say output current in the resistive load has exactly same waveform shape as of voltage across the load or resistor. That is what in the earlier voltage shift load, current shift load comparison. Okay. Therefore, what I can say here, output current I0 will also have the same waveform shape as of output voltage. That means the peak value is Vm by R. Only peak value is different. But both of these two waveforms, V0 and I0 waveforms, will have peak values at pi by 2. Okay. Next, from 0 to pi, as the device is in conduction, we can draw voltage across the diode is equal to 0. Okay, we can draw voltage across the diode is equal to 0. Next, another important point is, yet omega t is equal to pi, we can notice here that current flowing through the circuit load, which is also flowing through diode, is 0. Then what is the conclusion here? Just after pi, source voltage has negative half cycle, yet pi diode current is having 0 crossing. Therefore, we can safely consider diode is to be turn off switch. Then what will happen? Diode can be replaced with an open switch. So current flowing through that open circuit will be 0. Okay. And what about voltage across the load? I0 into R, that will also be 0. That will also be 0. So V0 and I0 both are interrelated. Okay. And both will have same waveform shape. Both will have peak values at the same instance. That is why we classified this under voltage shift load category. Now, from 2 pi to 3 pi, again the same waveform will repeat. Therefore, 2 pi to 3 pi, V0 waveform is the same as source voltage. I0 waveform will follows V0 waveform. That is what V0 and I0 waveforms. Now, what about voltage across diode waveform? From 0 to pi, diode is in conduction, and hence voltage drop across the diode is a 0. Pi to 2 pi, what will happen? Diode is in the off state. That means the entire negative half cycle of source voltage will appear across anode to cathode terminals of the diode. So this negative half cycle of source voltage will appear across voltage across the diode. Okay, negative half cycle of the source voltage will appear across a diode. This particular value is same as source voltage peak. Okay, and this value is used to refer peak inverse voltage. That means how much voltage the device need to withstand during its turn off conditions. and from 2 pi to 3 pi, as diode is again in the conduction, voltage drop across the diode will be 0. Okay, this is a simple circuit. These are the waveforms for single phase half wave uncontrolled rectifier with resistive load. Now, few important conclusions that we need to write down from these waveforms. Now, observe carefully, from where to where diode is in conduction. That is the first question. I can say that diode is in conduction from 0 to pi. So, conduction angle will be represented with a symbol called gamma. Therefore, gamma D is equal to, I can write gamma D is equal to pi radian. Okay. Next, see, these angles, whether it is in radian or degree, is also very important. During the numerical substitution, this angle substitution in degree or radian, if you substitute wrongly, you will get wrong results. Okay. Next, from this waveform, one more observation is I naught is maximum yet omega t is equal to pi by 2. I naught is maximum at omega t is equal to pi by 2. A third observation is peak inverse voltage is equal to peak value of source voltage. Now remember here, PIV, while writing PIV, no need to use a minus symbol, because the terminology itself inverse is already included. Basically, this PIV is used to select device voltage rating. Even 1 or 2 volt error is also not, no need to worry about that, because once VM is identified, we will take as a factor of safety 1.5 or 2 times of that value. Okay, therefore we will be in the safe position. Now let us see few basic equations from these waveforms. That is, as a waveform is a DC waveforms, the first calculation could be average. First time let me write completely. Average output voltage. Average output voltage, capital V naught, is equal to, the periodicity is 2 pi, hence 1 by periodicity 1 by 2 pi. What are the limits? That is from 0 to pi, Vm sin omega t d omega t. Okay, 1 by 2 pi integral 0 to pi Vm sin omega t 0 to d omega t. Integration is with respect to x axis. Now let us simplify this. V naught is equal to Vm by 2 pi integration for sin omega t is minus cos omega t, the limits from 0 to pi. Okay, 0 to pi. So if you substitute the limits, Vm by 2 pi, upper limit minus cos pi is 1, minus of minus plus cos 0, that is 1. So it is 2. Therefore, the final conclusion is V naught is equal to Vm by 2 pi into 2. So 2 will cancel out, hence it will give you Vm by pi. This is the expression for average output voltage. Okay, next. And average output current I naught can be expressed as V naught by R. If you substitute V naught value, we will get Vm by pi into R. Next. Now, as the load is resistor, how can we define output power? VOR square divided by R. Therefore, in order to find output power, we should calculate RMS voltage first. VOR square is equal to 1 by 2 pi integration from 0 to pi Vm square sin square omega t d omega t. Therefore, it will give you Vm square divided by 2 pi limits from 0 to pi, sin square omega t is 1 minus cos 2 omega t divided by 2 d omega t. Okay. Next, Vm square by 4 pi, integration for 1 is omega t minus cos 2 omega t integration sin 2 omega t divided by 2. The limits are from 0 to pi. Next, VOR square is equal to Vm square divided by 4 pi. Upper limit minus lower limit is pi, minus sin pi and sin 0 will be 0. Leave that. So pi and pi will cancel out, and if you take a root for this, RMS voltage is equal to Vm square divided by 2. Vm divided by 2. Now final expression for output power, Vm square by 4 divided by R. Vm square by 4R. And you can also write here RMS current is equal to RMS voltage divided by resistor. Now in this particular circuit, as completely series circuit, you can also write here RMS value of the output current will be same as that of RMS value of the source current. Okay. So this is about a single phase half wave uncontrolled rectifier with a resistive load. We'll take more loads in the foregoing lectures. With this, I am concluding this lecture. Thank you.